When a computer sends data to another computer, it is like sending a letter across a windy road. The wind noise can flip some letters' tier parts or even add extra bits. Error detection is the method the sender uses to check if the letter arrived exactly as written. The sender adds a small extra piece of information called a check value that summarizes the whole message. The receiver recomputes that summary from the received data and compares it to the check value. If they match, we assume the message is clean. If they differ, we know something went wrong. This is similar to putting a simple "I promise this package is untouched" tag on a parcel. If the tag is damaged or altered, the recipient knows the package may have been tampered with. A checksum works like adding up the numbers on a grocery receipt and writing the total at the bottom. The algorithm usually works like this. Step 1. Break the data into equal size blocks, often 16-bit words. Step 2. Add all the blocks together using modular arithmetic. That is, keep only the lower bits of the sum and discard overflow, just like the odometer rolls over after 9999. Step 3. Take the one's complement, flip all bits of the final sum and store it as the checksum. Example, suppose we send 4 8-bit bytes, 0x45, 0x23, 0x7, 0x01. Add first two, 0x45 plus 0x23 equals 0x68. Add third, 0x68 plus 0x7 equals 0x10f. Keep only 8 bits, that is 0x0f, and add the overflow 0x1 back. 0x0f plus 0x01 equals 0x10. Add fourth, 0x10 plus 0x01 equals 0x11. 1's complement, tilde 0x11 equals 0xEE. The checksum sent is 0xEE. The receiver repeats the same steps including the checksum. The final result should be 0xFF, all ones. If not, an error is detected. The math is simple. Checksum equals tilde sum I equals 1 to n of word I modulo 2 to the m, where m is the word size. A cyclic redundancy check CRC is like a secret handshake based on polynomials. Imagine each block of data as a long string of zeros and ones. We can treat that string as a binary polynomial where each bit is a coefficient 0 or 1 of a power of x. For example, the bit pattern 1101 becomes the polynomial x cubed plus x squared plus 1. A generator polynomial g of x is a fixed polynomial agreed upon by sender and receiver. For example, g of x equals x cubed plus x plus 1 for a 3-bit CRC. The CRC algorithm divides the data polynomial after appending 0 bits equal to the degree of g of x by g of x using binary mod 2 division, which is the same as exclusive or without carries. The remainder of this division becomes the CRC value. The beauty is that binary polynomial arithmetic lets us detect many patterns of errors, with only a few extra bits, much like a unique fingerprint of the whole message. Append zeros. If the generator polynomial has degree r, add r0 bits to the end of the data. This reserves space for the CRC. Polynomial division. Treat the extended data as a binary polynomial d of x. Perform modulo 2 division by g of x in hardware. This is just a series of shift registers and exclusive OR operations. Remainder. The division leaves a remainder r of x with degree less than r. Those r bits are the CRC value. Send, transmit the original data followed by r of x. Sample walkthrough. Use 8-bit data hex C2, which is binary 11000010, and generator g of x equals x cubed plus x plus 1, binary 1011 degree 3. Append 3 zeros, binary 1100001000. Align divisor 1011 with the leftmost one and exclusive OR. Binary 1100001000, divisor 1011 shifted left 7 positions. Exclusive OR yields binary 0 1110001000. Continue shifting the divisor to the next one, exclusive OR, and repeat until the remaining bits are fewer than 4. Final remainder after all steps, binary 0 10. So the CRC bits are 0 10, and the transmitted frame is binary 110000100010. When the receiver repeats the division on the whole frame, The remainder will be 0 if no error occurred. Explanation: choosing a good generator polynomial is like picking a lock that is hard to pick for certain kinds of attacks. Hamming distance: this is the minimum number of bit flips that can change one valid code word into another. A generator that gives a Hamming distance of 4 can detect any 3-bit error and correct 1-bit errors. The distance depends on the polynomial's properties. Burst error detection: a burst error is a consecutive run of corrupted bits. A CRC with degree r will always detect any burst error shorter than r plus 1 bits, because such a burst cannot be a multiple of the generator polynomial. Practical choices: Ethernet uses CRC32 with generator. G of x equals x to the 32 plus x to the 26 plus x to the 23 plus x to the 22 plus x to the 16 plus x to the 12 plus x to the 11 plus x to the 10 plus x to the 8 plus x to the 7 plus x to the 5 plus x to the 4 plus x to the 2 plus x plus 1. It offers a Hamming distance of 4 and detects all burst errors up to 32 bits. For smaller frames, CRC8, for example, x to the 8 plus x squared plus x plus 1 is common in automotive CA/N buses because it balances detection power with low overhead. When we compare CRC and simple checksum, we look at 3 factors. Detection capabilities. A checksum can miss many error patterns, especially if 2 errors cancel each other out, for example, flipping a 1 to 0 in one byte and a 0 to 1 in another. CRCs are mathematically proven to detect all single-bit errors, all double-bit errors, any odd number of bit errors if the polynomial has a factor x plus 1, and all burst errors up to the polynomial degree. This makes CRCs far more reliable. Overhead: both add extra bits, but CRCs typically need more, for example 32 bits for CRC32 versus 16 bits for a classic internet checksum. However, the extra bits are small compared to typical payload sizes. Computational complexity. A checksum is just an addition and a bitwise complement, very cheap. CRC requires polynomial division, which in hardware is just a shift register with XORs, and in software can be done with table lookup methods, for example 256 entry tables that are still fast. Modern CPUs have instructions, for example CRC32C, that compute CRC in a single cycle, making the cost negligible. Overall, CRCs give much stronger error detection for a modest increase in computation and a few extra bits. Network protocols embed the error detecting code directly into their frames. Ethernet: every Ethernet frame ends with a 32-bit frame check sequence. FCS: the sender runs CRC32 on the whole frame, excluding the preamble, and appends the remainder. The receiver runs the same CRC. If the result is 0, the frame is accepted. TCP and UDP both use a 16-bit internet checksum. The algorithm treats the segment as a sequence of 16-bit words, adds them with one's complement arithmetic, and stores the one's complement of the sum in the checksum field. When a packet arrives, the receiver adds all words including the checksum. A result of hexadecimal FFFF means the packet is error-free. Implementation details. In software, the checksum is usually computed with a loop that adds 16-bit words and folds any overflow back into the lower 16 bits. For example, sum equals open parenthesis sum bitwise and hexadecimal FFFF close parenthesis plus open parenthesis sum right shifted 16 close parenthesis. For CRC, many stacks use a pre-computed 256-entry lookup table. Each incoming byte updates the CRC as CRC equals table open bracket CRC XOR byte bitwise and hexadecimal FF close bracket XOR open parenthesis CRC right shifted 8 close parenthesis. Hardware network interface cards often compute CRC32 on the fly as bits stream out of the Mac, requiring no extra CPU time. No error detecting code is perfect. Some patterns slip through. Checksum: if 2 bits flip in such a way that their numeric contributions cancel, for example 1 0 to 1 and another 1 to 0 in the same weight, the sum remains unchanged. Also, swapping 2 16-bit words does not change the checksum because addition is order independent. CRC: a CRC will miss an error only if the error pattern is a multiple of the generator polynomial. For a well-chosen polynomial, the probability of a random undetected error is about 2 to the minus r, where r is the degree. For example, 1 in 4 billion for CRC32. Certain structured errors, like a burst longer than r that exactly matches the polynomial, can be missed, but such coincidences are extremely rare in practice. Both methods cannot correct errors, they only tell you that something is wrong. Higher-level protocols, for example TCP retransmission, handle recovery. How to pick between CRC and Checksum depends on what you need. Small low-power devices, tiny sensors, microcontrollers, may favor a simple 8 or 16-bit checksum because it uses very little CPU and memory, and the payloads are short, so the chance of an undetected error is acceptable. High-speed or safety-critical links, Ethernet, storage, automotive CAN, require the stronger guarantees of a CRC, even if it means a few more CPU cycles or extra bits. CRC32 or CRC16 is common here. Resource constraints. If the platform has hardware support, for example a CRC instruction, use CRC. If not, and the data rate is modest, a software checksum may be simpler. Error environment. In noisy radio links where burst errors are common, choose a CRC whose degree exceeds the typical burst length. For mostly clean wired links, a checksum might be enough. In summary, ask 3 questions. Number 1, how many extra bits can I afford? Number 2, how much processing power is available? Number 3, how risky is an undetected error? The answers guide you to a lightweight checksum for constrained, low-risk scenarios, or a robust CRC for demanding, high-integrity applications.